A soil mass is the huge collection of soil particles we call soil grains. These soil grains, when depositing in a soil mass, encloses empty space between them, which we call voids. The water available under the ground moves inside the soil through these voids from the region of high hydraulic head to the low hydraulic head. This phenomena of flow of water, movement of water through the soil, is called seepage. The hydraulic head is the amount of mechanical energy or liquid pressure available at any point in the water above datum. In the previous video of seepage, we have considered only unidirectional and linear flow of water inside the soil mass. But in many soil engineering problems, like the flow in the soil under masonry dams is multidimensional. As a soil engineer, our aim is to analyze the flow of water inside the soil and try to obtain the solutions to the engineering problems faced. One such problem is to estimate the quantity of water percolating via seepage through the soil under a dam. To solve such problems and to analyze multidimensional flow in soil, we make use of a concept called flow net. A flow net is a graphical representation of how the hydraulic energy is dissipated as water flows through the pervious medium. To understand the flow net, let's begin with analyzing one-dimensional flow before jumping into the multidimensional space. Let us consider a soil sample of length L and put it into a glass cylinder. We attach the top of cylinder with the water source and let the water flow through the soil and let it exit from the bottom. We also attach few piezometers at different depths. We can observe the flow of water occurs vertically downward under a head difference of say h. Any water particle that enters into the soil at its top moves vertically downward, and the path taken by this water particle can be represented by a line. That line is called the flow line. Similarly, many particles will flow vertically downward and there will be infinite number of flow lines. But for our convenience, we draw only few. These flow lines are also called streamlines. Now we can observe that at this level, total head is same for all the points lying in this plane. So we can draw a line connecting all the points of equal head. Similarly, at different levels, such lines of equal heads can be drawn. These lines are known as equipotential lines. All the points on an equipotential line have the same energy. Both of these lines, flow lines and equipotential lines, are crossing each other at right angles, and we say they are orthogonal to each other. We can see these lines form a kind of net, and this net is called flow net. A flow net gives a pictorial representation of the path taken by the water particles and the head variation along the path. This is a very simple flow net, and it is only for unidirectional flow in soil. But for multidimensional flow, the flow net may be very complex. Generally, the flow of water in soil is three-dimensional, and analysis of such flow is too complex and difficult. So, we simplify the flow situations to the two-dimensional and analyze the flow. Okay, then how do we construct a flow net for two-dimensional flow? Well, there are some methods for obtaining it. We will briefly discuss only these two methods. Analytical method requires a good understanding of mathematics and computers and particle accelerator. Analytical method of obtaining a flow net for a flow of water in a soil mass is a mathematical solution to an equation that is obtained by the flow conditions. It can be used in relatively simple cases of flow, where the boundary conditions are known and can be expressed in equations. Let's consider a soil mass which is completely saturated by the water flowing through it. We assume the velocity of water in x and z direction are Vx and Vz respectively. Let us consider a small soil element of dimension dx, dz and dy. Y direction is normal to the plane. Let's say water is flowing in the soil because of hydraulic head H, and the hydraulic gradient in the x and z directions are Ix and Iz respectively. Water is not flowing in y direction as we are analyzing flow only in two dimensions. Now, using continuity equation, we can write the amount of water going in this soil element is equal to the amount of water coming out of it. Remember, it is a simplified model. Well, somehow after solving it, we arrive at a simpler equation of continuity. After applying some assumptions, like the Darcy's law is valid, we can write as velocity of water as permeability times hydraulic gradient, where hydraulic gradient across this element is del H by del X and del H by del Z. So, next assumption is, if the soil is isotropic, then permeability in X direction is equal to the permeability in Z direction. So, finally we arrive at this neat and clean partial differential equation. This equation is called Laplace equation. But what do we have to do with this equation? Well, this equation describes the loss of energy through this space. And in our case, the energy is hydraulic head. When we solve this equation, we receive two families of curves. One set of curves is known as flow lines and other set is equipotential lines. Flow lines are also called psi lines and equipotential lines are called phi lines. Once we get these lines, we get our flow net and we can calculate our desired quantities like seepage through the soil. But for that, first we need to solve this equation, which is very easy. Even a computer can solve that. So we try to obtain our flow net for two-dimensional flow using next method, graphical method. This is the most commonly used method of flow net construction because it is easy and it provides nearly accurate results. This method is one of the solutions of the Laplace equation. Let us understand this method by drawing a flow net for a hydraulic condition. This is a soil mass of some thickness and it lies upon an impermeable strata. A sheet pile is driven into the soil up to some depth. The sheet has water on its one side of depth capital D and on the other side of depth small d. We can see there is an imbalance of head on the different sides of the sheet pile. So water will flow from high head to low head. But water cannot pass through the sheet pile. So flow will take place through seepage via soil below. Let us consider a water molecule enters the soil at some point on the upstream surface, goes below the tip of the driven sheet and ends up at some point on the downstream surface. The flow path assumed by the water molecule is the flow line. Similarly, many particles will leave the upstream and reach the downstream, forming different flow lines. Note that each flow line begins from the upstream surface, which is at pressure gamma W capital D, and travels through the soil, constantly losing its energy, and terminates at the downstream surface, which is at pressure gamma W small d. So, we can pick up certain points on the different flow lines where the total energy lost is equal. Or we can say points of same energy level. When we join such points together, the line so formed is an equipotential line. Similarly, different points of the same energy on different flow lines can be observed and many such equipotential lines can be drawn. If we insert piezometers into the soil at different points along an equipotential line, we will notice water rises to the same elevation in all the piezometers. We can see we have received our flow net. The space between two adjacent flow lines is called the flow path or flow channel. And the area enclosed between the two adjacent flow lines and adjacent equipotential lines is called flow field. In a flow net, we can draw many possible flow lines and equipotential lines. But first, it is very inconvenient to draw too many of these lines. And second, drawing too many lines does not increase the accuracy of calculations. So, only 4 or 5 flow channels are sufficient. To draw a meaningful graph, we need to keep in mind certain characteristics of the flow net. First, two flow lines can never cross each other because flow in soil voids is considered laminar. Similarly, no two equipotential lines can cross each other because if they cross at any point, then the total head at that point will be two values, which is not possible. Second characteristic of the flow net is that flow lines and equipotential lines are orthogonal to each other. That means they should intersect each other at right angles. Third, the ratio of the length and width of each flow field should be constant. Generally, we take this ratio as a unity for convenience. In other words, the flow net consists of approximate squares that are called elementary engineering. Elementary squares. In elementary squares, the average distances between opposite sides are equal. To construct a flow net, we also need to identify the boundary conditions present for the flow. Boundary conditions are the restrictions that limit the flow in a certain space or area. A flow net is unique for a given set of boundary conditions. If the geometry of the flow space changes, the boundary conditions will be changed and hence the flow net will be changed. Here, first boundary condition is the upstream surface from where the flow starts. And if we notice, it is the first equipotential line of our flow net, as at every point on this line, the total head is same. Second boundary condition is similar, and that is the downstream surface. It is the last equipotential line of our flow net. The third boundary condition is this sheet pile. Water molecules cannot cross the sheet. It flows from this point vertically downward, and after crossing the sheet pile, it will vertically ascend. This line is also tracing the flow path of the molecule, so this boundary, if we name it ABC, is a flow line. Fourth boundary is the impermeable surface. Water molecules cannot cross it. This line is also a flow line, as the water will flow along this surface from this side to this side. While drawing a flow net, we also need to keep in mind that no flow line can intersect the impermeable boundary, as the impermeable boundary is itself a flow line. For the same reason, all equipotential lines must meet the impermeable boundaries at the right angles, because impermeable boundaries are flow lines and flow lines meet equipotential lines at right angles. These equipotential lines are drawn in a way that drop of head or loss of head between two adjacent equipotential lines is constant, which means if head at the first equipotential line is 15 meter and after the first equipotential line that head has dropped by 2 meter, so next drop in head should also be 2 meter, and so on. Also, the discharge between two adjacent flow channels is constant. Now that we have constructed the flow net, its graphical properties can be used to calculate the seepage through the soil. Let's say height of this flow field is small a and length is small b. We know from Darcy's law that discharge through flow field can be written as this. Here, K is the permeability of the soil, A is the area of cross-section through which the water is flowing, which is height of the flow field A multiplied by its width, say W. But it is generally taken as 1 meter. I is the hydraulic gradient, which is head loss over the length of the flow field B, say delta H. So, discharge through this flow field can be written as this. Now, delta H is the head loss through this flow field, or we can say drop of head or potential drop through this field is delta H. And let's say there are number of such drops, potential drops is ND. Then total potential drop or head loss through this whole flow channel is ND times delta H. Let's substitute this in equation to find the discharge through one flow channel. Note that this is one potential drop between two equipotential lines, and these are two potential drops between three equipotential lines. So we can see number of equipotential drops ND will be the number of equipotential lines minus 1. Again, this is the discharge through one flow channel, and if total number of flow channels in the flow net are NF, then total discharge can be written as NF times discharge through one flow field. Remember that flow net is constructed by elementary squares, so this quantity is 1. So total discharge through soil can be written as this. This ratio is called shape factor. So this is how we calculate the seepage through soil under any structure using flow net by graphical method. We know that for a given set of boundary conditions, the flow net is unique. It is dependent on the boundary conditions. If boundary conditions changes, the flow net will also change. But if we change the soil in which the water is flowing, the flow net will not change. Only the permeability of the soil, K, will change. Flow net will also remain unchanged even if the upstream and downstream water levels are reversed. Only the direction of the flow will be reversed. We can use the flow net to find solutions to our engineering problems, such as the estimation of quantity of seepage losses from reservoir, determination of seepage pressure, uplift pressure below dams, and to check the possibility of piping and many others. Take a look at an example of seepage calculation with FlowNet on elementaryengineeringlibrary.com. If you like elementary engineering videos, you may support it on Patreon. Like that, Cyborg? Well, you can buy that poster on Professor for your living or study room. Also, check out Elementary Engineering's handmade diaries there. Read FlowNet on elementaryengineeringlibrary.com. All the links are in the description. Thank you.